Let us talk about this problem. We need to write a recursive function that takes an integer n as an argument, and this function prints all the integers from n to 1. For example, if n is 5, then it prints 5, 4, 3, 2, 1. If n is 2, then it prints 2 and 1. You may assume that n is greater than equal to 1. User is never going to provide 0 or a negative number. Now please pause this video and try to write down a recursive function. The idea to solve this problem is to again think in terms of smaller problems. We need to see if we have solution for a smaller problem, can we use it to solve the overall problem. We wish to print n numbers here from n to 1. Now if I have a solution that prints numbers from n minus 1 to 1, then I can use this solution and I can call this solution. I can print n on the screen and then call this recursive solution. That's the idea to solve this recursion. Now the question arises, when do we stop? Suppose you want to print first 4 numbers from 4 to 1. So you will print 4, then you will call for 3, then you will print 3 and call for 2, then you will print 2 and call for 1, then you will print 1 and call for 0. So when you call for 0, you can't proceed further and you don't want to print for anything for n equal to 0. So we return when n is 0. This is our base case. Now please pause this video and try to write down the complete code. Let's now take a look at the implementation. So we have a base case which says if n is equal to 0, then don't do anything. Otherwise, print n and recursively call for n minus 1. Use the solution for a smaller problem. So when you call print n to 1 for 4, it prints 4 and calls for 3, it prints 3 and calls for 2, prints 2 and calls for 1, prints 1 and calls for 0. And this is where this execution stops because n becomes 0, so it does not make any further recursive calls. So it immediately stops and gives the control back to the caller. Caller has nothing more to do, so caller also stops and then gives control back to the caller. Caller also has again nothing more to do because the recursive call was the last thing, and so on. So finally you get the output as 4, 3, 2, 1. Now talking about the time complexity of the solution, you can notice that there are n plus 1 function calls and every function call is doing some constant amount of work. So this is how we can say time complexity is theta n. If we wish to write a recurrence relation to know the time complexity, we can say it's tn equal to tn minus 1 plus theta 1. Theta 1 is constant. So every function does constant amount of work and then makes a recursive call for tn minus 1. If you solve this recurrence using recursion tree method, you will get the value as theta n. Now talking about the auxiliary space for the solution, there will be a situation where you will have n plus 1 function calls in the function call stack. When you call print n to 1 for 0, so 4 has called 3, 3 has called 2, 2 has called 1, 1 has called 0, and these functions are waiting for their children to finish. 4 is waiting for 3 to finish so that it can resume its execution, it can also finish. So there would be a moment where you will have n plus 1 function calls in the function call stack, so we can say its auxiliary space is theta n. However, we are going to talk about a concept called tail call elimination, and if your compiler is a modern compiler and does tail call elimination, then auxiliary space would reduce to theta 1. We'll talk about tail call elimination and tail recursion in a video.